multi-messenger approach in data analysis of core collapse supernova.
Okay. Can you hear me? Thank you. Okay. So, of course, my talk is multi-messenger, but I'm a little biased about gravitational waves, so forgive me for that. And what is the... there. So when we speak about multi-messenger, we all know more or less why we want to do multi-messenger. In the sense that most of us, all of us remember what happened in 2017 when we had multi-messenger of gravitational wave and electromagnetic, and we discovered the binary nuclear connecting. And there was a very exciting moment for everyone of us. And actually, for just one event, we have a new discovery excitement that was not was imagined before, but we were not sure about that. For instance, it was a good estimation of the travel of the gravitational wave. We proved that short company paths are produced by electron merger and so something like that. We also tried to mention the H note that, of course, was not real life, but it proved the fact that the multi-message is a really good stuff that should be done by us. We also never forget the fact that the first real multi-message detection was the supernova of 87. Unfortunately, it was not given by gravitational waves. At that time, there were the astronaut parts that had to do, but was not possible. But it's also given by other talks in this symposium. We had the fact that also in that case, there were new discovery and proof about the theory, and some theory were discarded. And also, we went to the proof that the supernova produced a neutrino. In fact, it was the first time that. So what are in summary the advantages when we want to do a multi-messenger detection? Of course, we can increase the detection confidence. If we speak especially about the wave, if we have all the gravitational wave detection, maybe the first one can be a little tricky because we don't have a huge or a big first run rate. But if we have, of course, a neutrino and electromagnetic together, the detection is just a little increased. The sky localization that is important, of course, because we can identify maybe the object that produces the galaxy, what it is. Maybe we can try, if we have the luminosity also, the convoluted distance, we can try to estimate the zero, something like that. So we can do a lot of exercise. And of course, if we have a multi-messenger, we can try to characterize better the source. For instance, giving some information from gravitational wave and other information from, for instance, neutrino, and of course there were other talks. There were other talks in this symposium, and there will be also other that explain some example of that. So another question is who we are interested in multi-messenger. This is just a slide because I want to make all the answers, because multi-messenger sources are all that type of sources that produce, for instance, gravitational wave. So they have the quadrupolar motion. And practically there is an involvement of at least a not black hole stuff. So these are some examples. But of course, this symposium is about supernova, so we don't care about anything else for now. So I just report this. But before going on, I want to make a little digression about the stuff, how we work very basic in gravitational wave when we try to make a search. So the idea is this, if we consider a certain amount of time, that in our case is very short, in principle, the signal could be there or not. And we can make what is called a decision rule, that usually are algorithms. But in principle, can be everything, like throw dices or ask to some octopus that sometimes they can do that. And you can decide that there is or there is not a signal. Of course, if you combine the truth and your decision, you have two cases you are right and two cases you are wrong. In the linear world, what you want is that the red one is 1, and the red case is 1, and blue case is 0. Of course, it never happens because the world is not like that. But imagine you have a different decision rule, and you want to decide what is the best for you. And there is a criterion that is called the name person criterion. That okay, if you are comparing different decision rule, the better between the best one is that given the greater true alarm rate at the same false alarm rate. So just decide, say what are we talking about? What is the true alarm? The true alarm is the efficiency, practically. So the idea is that when you have a real signal and you say your decision rule say that is there. How we do that, in principle, is easy to do in the sense you make some fake signal in your data. It can be supernova signal, whatever type, or also compact binary correction, depends what you are interested. So you put in the signal, and it's the case there. Oh. And you just apply your decision rule, and you see how many of them your decision rule accept. So in this case, your true alarm is 50%. And of course, you can do this according to the parameters of your gravitational wave in this case, or whatever source. Instead, you can characterize your efficiency according to the frequency, according to the distance, according to the parameter, the mass of the progenitor, or whatever it happens. The false alarm is a little tricky in the sense it can be it's not so easy to do. And what we do in gravitational wave, maybe you already know, but a short summary is just useful sometimes. Imagine you have two detectors, in this case the LIGO one. You know that they are far apart of 10 milliseconds more or less travel time. And imagine you have two different signals that survive your decision rule. They are, of course, they can be given by gravitational wave in this case if they are far maximum apart of 10 milliseconds. The other are not possible from the theory. The problem is that are these two a real signal or are just excesses of noise that for chance they are in coincidence? And what we do to decide that is to do the usual time shift procedure. You time shift your data of more than 10 milliseconds, better to do maybe more, so they are not correlated. And every time these are, if you think that is not shifted, every time these are connected by 10 milliseconds, this for sure they are not real gravitational waves at the same time, but they are just coincidence that happen for chance. If you repeat this multiple times, you have like an example of what is your original data, the line 0. So imagine that it happens every time, 10 times for every time. So you can say that you will expect 10 times also here. If here you have 20 signals, you can expect that they are real gravitational wave. So this is how we calculate the false alarm. And then just a short part, if we speak about supernova, given the fact that we don't have exhaustive supernova models, we have to be open to algorithms that can detect whatever are confident with gravitational waves. And so the example are coherent wave burst, X pipeline. Oh, this should be also bias wave. Maybe it's not the updated stuff or something like that. What is the main limiting factor, particularly the SNR? Because what you are searching is something that is a little above the noise level, practically. So it's not a matching filter that you can dig, but that you are limited practically by that. So you have to try to decrease and try to not be affected as much as you can by the noise excesses. But about this, I'm sure that there will be, like Sergey having tomorrow, better explanation of that. Just a little part about the source localization. Other people already say that. So the main algorithm to calculate the sky position is triangulation. So imagine you have two detectors. You have a circle in the sky. But luckily, as Lady Michele explained days ago, we have the antenna pattern that excludes some of the circle in the sky. So usually you have a part. If you have more than two detectors, you can localize better. You can have at least a spot in the ring. So this is why, for instance, if we compare the first event only or one and or two, I reported the few, otherwise we are mess here. When you see an arc in the sky, it's two detectors working. When you see a spot or similar to a spot, it was 3 detector work with. So more detectors, more is better. That's what you can expect from here. So going on, where and when. So now I'm going to the GW point of view, in the sense that all the terminology that we use is compared to GW. But imagine you have search of GW and search of other stuff. There are different ways to do multi-messenger. One is that when you have a trigger from neutrino or electromagnetic, what is called trigger stuff, and you search for gravitational wave at the same time and or the same region. And this is what we are doing from long term, in the sense that also Yang already explained you 2 days ago, so I don't want to go in detail. But you just search the same sky direction and the same time given by the other messengers. Like this is a figure taken from taken from the search from GRB trigger, because also, for instance, long GRB can be produced by supernova. So this is something that we can do. And the simple explanation for that is that if you know the sky position, the time, practically, in short, you are reducing the false alarm rate. And then you can increase also the confidence, something like that. But the 0 point is that you reduce the path. And of course, you can increase the efficiency because you are focalizing that path. Another point of view is that when you know gravitational wave, the trigger, and you search with the other messenger, this is the follow-up part. That, of course, all of you already know how it's working, because also every day when the detectors are on, we submit the trigger to the GCN, and people can try to do that. Some example that we also did in the LIGO collaboration, for instance, that using neutrino part, this is, for instance, the sky map of the GW15 on I14. And at that time, there was making a search with the neutrino part with ice cube. Of course, you can see that at the same time with a window that now I don't remember, practically the sky map was not connecting, so there were no follow-up part. And another time, just for joke, is that in principle, the binary neutron star, the gamma ray burst arrived later. So in principle, it's a follow-up of gravitational wave, but it's just a joke because it's not true. Because we know that the real search was done together at the same sky position, and also the fact that Fermi, integral, and LIGO Virgo had the same region in the sky at the same time was a higher confidence of the fact that it was the same signal. Last point, but not least, of course, is time to do a joint search. So we don't have really neither gravitational wave, neither neutrino, neither electromagnetic, but we try to dig in the noise of both of the three to enhance the detection of all of them together. And one example, for instance, is this part that this is also inside the LIGO collaboration. We try to search for neutrino ice cube low trigger and gravitational wave low trigger together that occur at the same time, and also the same sky map probability, in the sense that the two sky map are let's say multiplied together to enhance the fact that there is the same probability coming from the two directions. Of course, neither of these search is given unfortunately a result, because otherwise we all knew that, but it's another type of search that we can do. So last part of the presentation is what else we can try to do. So this is just an overview of some search approaches that was not already mentioned before, and the one that I remember for myself. So apologize if this is not complete. Don't be offended if you are not in these slides. So one example is that, for instance, was done between neutrino and gravitational wave. This is about 2021. And it is what we can part of the joint search, in the sense that you get the trigger from gravitational waves, and you get the trigger from super K, if I remember correctly. It's not written in the slide. And you have a coincidence, particularly the main part was to make a coincidence between the false alarm rate of the two triggers. You have a window in time. So in principle, theoretically, you can make a false alarm rate global between the two, just multiplying the false alarm, the single false alarm rate of the different. Of course, this can be extended to more than 2 searches. You can also add the electromagnetic part, because this should change particularly only this number. You have also to modify a little this part, but it's not really the best part, the difficult part. So theoretically you can do. The result of this analysis is quite tricky, because it shows that, for instance, you can use a low gravitational wave force alarm rate to combine with a high neutrino, and in principle you have a detection, because we know that the neutrino detection can be done at farther distance, easier than the gravitational wave for the detector we have now. So in principle, you can ask for a high force alarm rate of the gravitational wave and combine to have a very low combined global far. The problem is that in principle, when you have a very high force alarm rate, maybe you have a trigger that is in coincidence, but you are not really sure that is the supernova, actually. Because if you look at the trigger, maybe it's just noise that come in coincidence with that. So maybe the results give you that is good, but maybe it's not. So there are some pro and contra about this. Another example is answering to the question, what happens if it happens a gravitational supernova when there is only one detector point? And this, for instance, in the gravitational wave part is quite a problem, because usually it's difficult to make the force alarm rate analysis, something like that. So this is a work, and then also Marco was involved about that. And the idea is that use a search for supernova in only one detector working, and train on machine learning the CWB parameter to try to distinguish better between the background and the real signal. And this is an example. The blue is the background, the force alarm rate. The red is the injection of supernova. And the neural network is trained with all this information. You can see that for some of them, there is a good difference between the two. So it's really a nice idea to train for that. And there is also a result of the fact that you can decrease the force alarm rate even if you have only one detector. So it's a good strategy. Another example of using neural network or machine learning for supernova is that we all know that the high frequency part, it was explained in a lot of talks in this symposium, and this is more or less quite common for a lot of supernova explosions. So why not use this information to train a machine learning algorithm to try to recognize this? It's practically the same way to recognize cars when you read the numbers. And this was done in different papers. Another improvement about this is not using only this part, but is try to make a sort of RLG composition between the different detectors, because you can expect that when you have the same signal for different detectors, they should be increased the significance in the image. So there are little tricks that you can add. And the real question here is that how to train your machine learning, in the sense, since the waveform that you have maybe can be quite limited, in principle you should need to have the most extensive training set you can use. And this was helped by the fact that particularly Pablo was performing some model that are like a phenomenological model that reproduce this arc, this high frequency part. And you can see the paper for more details. And how these are used to train the neural network. And then, of course, they are also tested in the literature waveform to see if just using these approximate models can detect also the real part coming from the numerical simulation. And the results are promising. Of course, you are, of course, limited by the fact that in any case, the energy of the supernova is not the best higher of your life, and also the detector in any case are limited by the geometry and the sensitivity that can be delivered, but in principle you can try to increase your your detection range in this. This is, of course, a work in progress that can continue and maybe improve. Another things, I guess the last is another test that was done recently, trying to use the information between the neutrino signal and the gravitational wave signal, given the fact that we know that SASI in principle has some part in common between the neutrino detection and the gravitational wave detection. So try to use this fact to build a sort of matching filter between the neutrino part and the gravitational wave part. So given the fact that in principle neutrino we expect to be more easier to detect at the same distance, use the neutrino signal as a matching filter for the gravitational wave. Of course, you are limited by the fact that this is not like the compact binary correlation where the signal is really strictly very good model by this factor, but it's a little approximated. And also by the fact that in principle the frequency between the two are not the same, but are connected by a factor of 2. But this was a starting point. Indeed, you can see that it was tested only on one particular cases. They were explored also different directions in the sky, so they were strong and not so strong SASI modulation. And even if it is a really starting point in the sense it was new, build a sort of new algorithm taking the inspiration from the matching filter, but changing a little to try to fit the fact that we are not really have the matched part. It was a very beginning part, but it was promising from the fact that, for instance, compared to a simple, a usual excess power algorithm, at least for low distance, it was improving the detection efficiency at the same Fourier rate. So it was promising the fact that it can be a good strategy, but of course it needs to be explored more. What are the improvements that can be done? For instance, making better model for the matching filter, also exploring different progenitor model or something like that for the now was not, for the moment was not now. So these are the conclusions, but practically is just a summary of the previous one, so I don't want to go there. Just waiting. So we are practically ready in principle. We have a lot of different studies. We can improve, so we're just waiting for the supernova that happened this night, but or not, we don't know. So just waiting for that. And that's all for now.
Thank you. Questions? One more. Okay, so could you
Thank you. In one of the slides, you mentioned the GW 150914, the first binary black hole merger. So I'm curious, I didn't know whether some searches for the neutrino signal from that event, or you had it on the slide, or it's just that there were no neutrinos. I remember there were some claims about a gamma ray signal that was declined later on because only one of the gamma ray satellites detected something. Apparently it was not confirmed by the other satellite missions. What about neutrinos?
Now the neutrino in principle in the sense that I'm not the most expert on ice cube, of course. So if there are people more expert on me, feel free to add something. In the sense that there were some trigger from ice cube that were at the same time not the best confidence also to be true. So the idea was that similar to the one later, in sense if you have the same time and more or less the same distance, what is the probability to be not distance direction? Sorry, what is the probability to be the same signal? And you can just make a statistical calculation on that, and the results give you probability or not. In this case, was not probability was not enough to make a detection. So, but you expect in principle not to have other messengers from black hole. Otherwise, there are some accretion probability, something that can produce in principle, but we don't expect. So it's just a try. If you see something like the case that you were mentioning, that in the beginning was like probability and then they refuse. So you try to do that without expecting to have a results. For now, we didn't have results, apart some time spot, but not confirmed. So I hope I answered your question. Okay.
So I have a question about the time of the gravitational wave signal. So when we have gravitational waves from a compact binary merger, the definition of the time of the signal is like we have a standard definition and everyone understands what it means, right? So we have the time that we give everyone is the merger time, so everyone understands that's where the amplitude is loudest, the in spirals before that, the ring down is going to be after that. But for a supernova, I think when we say it occurred at this specific time, the gravitational wave emission, then it's harder to define what you mean by the time of when the signal occurred, because like, do you mean the core bounce time? Do you mean the time when we started to see the gravitational wave emission? Do you mean the time where the amplitude is highest? Do you mean the time that's in the center of the signal? So I wonder, like, how is the time that we would like give to the astronomers defined, and how do we make it clear what we mean by that time if we don't have a standard definition of time of gravitational wave for a supernova like we do for the compact binaries? Maybe this is a question for the discussion later. Maybe I don't know if you have all the answers.
No, I don't have, in the sense that it is a good question, in the sense that for now, how we work in the algorithm, when we say, for instance, equivalent with burst time, this is a mean time according to the likelihood. So it is practically similar to the time when you have most energy, but it's not really there. I mean, but it's for sure near to that. So in principle, when we give the time, we give the time, but we can be more complete in the sense that we can give the time between the start and the stop and the signal we found. We can give a lot of all the stuff that we want. We have to decide what we want to say and what is important to say, in the sense, but we don't have a clear definition on that for now, but it's something that maybe we have to decide among our group. Also, according to what theorists want to know better, in the sense they want to know what is the peak time, they want to know the start, how long is the signal. In principle, we can give everything, because if we compare, oh no, sorry. If we see this one, I'm lost. Yeah. If we see this one, you see here there is a different part of duration. This is low and high is referred to the starting and low frequency, high frequency. But you can also give the starting time, the stop time. Of course, it's limited by the fact that you can see. I mean, if you see 50% of the supernova signal, you can just say, I've seen this signal from this time to this time, and I'm not sure how much it is. So of course, this is probably limited by your results. So it can be almost complete information that we have that can be partial according to the real signal. So yeah, maybe it's something that we have to discuss between us.
Yeah, I agree that this is something that's going to be good to discuss more, because even from some of the other discussion, the better we know when the gravitational wave is emitted, the more efficient we can be in searching for that. However, for example, for the neutrino, I know if you know the timing, or if you define the time of the peak with 100 milliseconds accuracy or 10 millisecond accuracy, you don't get much more benefit for the gravitational wave, because the intrinsic duration of the gravitational wave is the order of a second long, so you can't shrink the window where you search much more below a second. So there are certain subtleties that I know you can't go over that.
Okay, any other questions to Marco? Then we're done. Thank you, everybody.
Okay. Hold on.